Atoms, ions, and molecules in a nutshell. So what are atoms, ions, and molecules and how they're all connected? So let's get started. So some historical stuff before we get into the specifics of molecules and ions. John Dalton, 1800s, said compounds always have the same ratio. So basically what that meant is that the thing you're breathing out every day, carbon dioxide, is always going to be CO2. It's always going to be one carbon and two oxygens. It's not going to be CO one day, CO2 another. It's the same ratio every time. That's basically his contribution. Next person we're going to talk about, J.J. Thomson. He said the atom looked like that little diagram right there, the plum pudding model. Basically, he came up with discovering the electron in 1897. And from that, he hypothesized that the atom looks like this. You have these basic electrons floating in this positive charge pudding, if you will. And that was the atom. There is no nucleus, as you can see. It is just positive charge, and there is these electrons embedded inside of them. So that's 1897. Rutherford came around afterward and said, the plum pudding model is wrong. He discovered what's called the nuclear model of the atom, which means there's a nucleus. The way he discovered that, he shot alpha particles at this gold foil. Now, gold foil is made a lot of atoms, and what should happen, if Thomson was correct, all these particles should go straight through because there's nothing causing them to change directions. What he found, though, that some of these particles actually came back this way, some got deflected, which means they must be hitting something. Since an alpha particle is positively charged, he hypothesized that whatever they're hitting is also positively charged. And because only a few of these actually changed direction, majority still did go through, that this thing was extremely small. So from here, he discovered, or he hypothesized the atom is positively charged, has a positive charged nucleus, and the majority of it is empty space. All right, some information you need to be familiar with as far as how information is represented for an element. So what we have here is basically the symbol of the element, and you have on the left, upper left-hand corner, whenever you see a number there, you always assume it's your mass. Bottom left is always going to be your atomic number, which represents your protons, and if the atom is neutral, also your electrons. If there's a charge, like let's say Ca2+, that goes in the upper right-hand corner. Subscript is how many. So, for example, let's say I go calcium phosphate. So we have a subscript next to the element. That tells you how many. So that's what the subscript represents. All right, some basics about the periodic table. You do need to be able to figure out the charges based on group numbers. All group 1 is always a positive 1. All group 2 is a positive 2. We skip transition metals because they have multiple charges, and that's represented by Roman numerals. Aluminum's group, positive 3. Nitrogen's negative 3, negative 2, negative 1. You'll see there's this red staircase that separates the metals from the nonmetals. On the left side, they're all metals, except hydrogen, which is technically a nonmetal. It's the only exception. And everything on the right side is actually a nonmetal. Things directly on the staircase are called semimetals or metalloids. Why do I point this out? So that you understand everything to the left of the staircase is going to have a positive charge, and things to the left typically have negative charges. And the reason I get these charges is because they're trying to get a complete shell. And you could, of course, figure out the number of electrons by looking at the charge and subtracting. For example, let's say we have Mg2+. That tells you, that 12 protons is guaranteed for magnesium because it's atomic number 12. But because it has a positive charge, you have to assume the 2 electrons were lost. And because of that loss, you're left with a positive 2 charge. That's how it comes about. So you get a positive charge when the atom loses electrons. So metals are basically losers because they always get positive charges. And nonmetals are the winners because they always get negative charges. Like, for example, oxygen. What it has, oxygen's atomic number 8, so it's got 8 protons. So how to get a negative 2 charge? It got 10 electrons. That's how it got a negative 2 overall. And why did it do that? Because when it gets 2 more electrons, it becomes like a noble gas, has what's called a complete shell. Isotopes, elements that have same number of protons but different number of neutrons, thus different masses. For example, let's say we have chlorine, or let's go with oxygen again. We'll go O, atomic number is 8. Remember, bottom number is your atomic number. Your mass, let's say, is 17. Let's say we have another oxygen, which has 18 and 8. Notice the only difference between these two oxygens is their masses. And why is the masses different? Because they have a different number of neutrons. So neutrons plus protons make up these masses. So here we have 8 protons. We have 10 neutrons, because 10 plus 8 gives you your 18. Here we have 8 protons and we have 9 neutrons. So you can see the difference between isotopes is they have a different number of neutrons and also different masses. Ions, on the other hand, as we saw earlier, are elements that have charges. That's because they gained or lost electrons. All right, these are polytemicons. These are compounds with charges. You have to memorize all of them. So you would have to know that thiocyanate, SCN with a -1 charge. You have to know peroxides, O2 with a -2 charge, and so on and so forth. So all these are required to just be memorized. There's no way around that. Because if I give you a random polyatomic ion and you don't know the charge, you're gonna have problems. With elements, you could just use a periodic table. Like if I told you calcium oxide, you're like, okay, that's calcium and oxygen. Use a periodic table, voila. But if I tell you calcium peroxide, if you don't know peroxide's O2 -2, you're out of luck. So these need to be memorized. Formula writing, we're going to do the crisscross method, which basically means that we take the element symbol. So here, magnesium's a +2. We look in the periodic table. Chloride's a -1 because it's group 7. Once again, you have to memorize these charges based on group numbers. And all we do is what's called the crisscross. We take the 2, put it over here, the 1 over here. It's basically a -1. So your formula becomes MgCl2. So we crisscross the top numbers and we bring them down. Notice I didn't bring the charges with them, just the numbers themselves. This is how you would write formulas for different compounds. And there's a whole screencast for this as well if you want to just focus on it. Tin 4 fluoride, same logic. We're going to take SN, +4, S, -2. We crisscross it. So when we crisscross it, it becomes SN2, S4. Now, the only thing about the crisscross method, these subscripts need to be reduced whenever possible. So here, there's nothing reduced, it's just 1 and 2, but here it's 2 and 4. So you can reduce this down to 1 and 2, so you get SN, S2. So whenever possible, you do need to reduce the subscripts for any formula writing. That's the one requirement of the crisscross method. You do need to reduce it. Iron 2 oxide, same thing. We're going to write Fe. Roman numerals, in case you didn't catch on, is basically your charge. So this is 4. That's why it's +4. This is Fe, +2. O, -2, crisscross again. Now, when it's the same number for both of them, they just go 1-to-1 ratio. You just write FeO. Because if you write it out, Fe2O2, these are basically the same number, right? So you have to reduce them. So you get FeO anyway. So if you have the same charge for both the cation and the anion, simplest thing to do is just make it a 1-to-1 ratio and move from there. And beryllium phosphate, now we have a polyatomic ion. So we have Be2+, PO4, -3, crisscross again. 3 goes here. Now the question is what to do with 2. You don't multiply, so you don't sit there and make it 2 times 4, which is 8, make it PO8. That doesn't work. You have 2 PO4s. So that means that you need to represent it this way. The way you want to look at this is that basically you have this inside your solution. You have Be2+, Be2+, and this tells the reader it's 2 phosphates, so PO4, 3-, PO4, 3-. Notice the total negative charge is -6, total positive charge, +6, you get 0. That's what you have to do for these ionic compounds. The charge has to balance out the 0. Now you could sit there and do this for every single formula, or just the crisscross, and just remember to simplify, reduce the numbers down. Choice is yours. I'd go with this crisscross. All right, naming ionic compounds. Compounds made of 2 elements are the first step we're going to go over. Metals from group 1A, 2A, and 3A or 13. 13 is the same thing as 3A, depending on which system you're using. Let's just put 3A instead of crossing it out. in any of those three groups, the charge is the group numbers. This is +1, this is +2, this is +3. So for those, you just name the cation and anion, there's nothing else. For example, NaCl is group 1, so just sodium chloride. Just name the cation, name the anion, call it a day. Magnesium chloride, same thing. If the anion always ends in ID for all these, unless it's a polyatomic ion, and even some polyatomic ions have ID as their ending, but typically your polyatomic ion has your ate and ite endings. Those are your typical two solute possibilities. But these are compounds only with 2 elements, so polyatomic ion is not part of this list. If it's a metal from any other group, use a Roman numeral. So if it's 1A, 2A, or 3A, just name the metal, you're done. If it's any other group, and I should make an exception for this, there's also 3 elements that don't abide by this. Let me first give you this. So you notice in each of these 2 situations, you have to indicate the name with a Roman numeral. The Roman numeral chart is representing the charge. And for those wondering how do you get the charge, you crisscross it. So this 3 is basically the charge on Fe, right? And the charge on chloride is -1. Same thing here, the charge on Fe is +2 and chloride is -1. Now, there are 3 exceptions to this. So we call it ZAC, easy to remember. So zinc is always a +2, silver is always a +1, and cadmium is always a +2. So these 3 actually belong with this rule. So in those 2 situations, 1, 2, 3, 4, 5, 6 situations, excuse me, you don't need to use Roman numerals. Any other time, you have to use Roman numerals. All right, if a compound contains 3 or more elements, you know there's a polyatomic ion, identify it, name it and what's attached to. So NH4Cl, you notice there's 3 capital letters, so you know there's going to be 3 different elements involved. So that's why ammonium chloride involves a polyatomic ion. Barium nitrate, same thing, 3 capital letters. Let's take a look at some examples of this. So what is this one? So strontium is group 2. So we're just going to call it strontium oxide. Notice no Roman numeral because it's from 1A, 2A, 3A, excuse me. For lead chloride, same thing, you crisscross it. So here, this is not 1A, 2A, or 3A, so the system's a little different. We got to uncrisscross it. So basically, if it's not 1A, 2A, 3A, or ZAC, you have to uncrisscross. And that means a little bit more work. So basically, lead becomes +4, chloride's -1. So you have lead 4 chloride. And here, this is group 2A, so just calcium nitrate. Notice I didn't have to worry about crisscrossing or anything else. So if it's group 1A, 2A, 3A, or ZAC, no one crisscrossing, really easy to name. If it's any other group, you got to do a little more work because you have to uncrisscross it. All right, covalent compounds, rules, you always end in IDE. Prefix is used to indicate how many of each element you have. So CO is carbon monoxide because there's 1 oxygen. Here are the different prefixes you have to memorize: mono, di, tri, tetra, penta, hexa. You probably recognize most of these from geometry. The only weird ones probably are going to be tetra. It's like, sounds like Tetris. And maybe deca and nona because you haven't used it frequently, but the rest come from geometry. You do need to memorize these because it's the only way to use the system. So anytime there's a metal and a non-metal, it's ionic compounds, use the system we just talked about a second ago. If it's 2 nonmetals, this is the system you need to use with the prefixes. So first one, P2O5, so that's diphosphorus. Notice I don't have to do any crisscrossing or anything cute like that. How many oxygen? Pentoxide, because there's 5 oxygens. Here, dichlorine. How many oxygens do you see? 7, so that's heptoxide. You notice I dropped the vowel from the prefix. There should be penta, there should be hepta. Whenever there are 2 vowels next to each other, you drop the 1 from the prefix. So instead of calling it pentoxide, you just call it pentoxide. Instead of heptoxide, just heptoxide. So you can't have 2 vowels next to each other. So rather than drop the vowel for the nonmetal, you drop it from the prefix. Here's some more. Carbon dioxide, that tells you 1 carbon, 2 oxygens, really easy. Tetraphosphorus trichloride, that's 4 phosphorus, so 4 tri. Pentacarbon monoxide. Pretty straightforward. Also, remember, you don't use the word mono in the beginning. This is not monocarbon dioxide. So if the first element, there's only one of them, just name it. You don't have to put mono. But for the second element, you do have to use the word mono if necessary. All right, precipitation reactions are reactions occurring where you mix 2 different solutions and you get a solid out of it. That's what precipitation is. So in order to do these, you have to know what the solubility rules are. So the solubility rules are basically 3 rules that's going to tell you if something is soluble or insoluble. So soluble, any compound involving ammonium, acetate, perchlorate, alkali metal, and nitrates are always soluble. So easy way to remember that, I am a soluble pan. You notice the lowercase letters just there for making the sentence. Capital letters represent the actual identities of the substances. So M will be ammonium, A will be acetate, P capitalized will be perchlorate, A is alkali, and N will be nitrate. So these are always soluble, always. That means that if these are involved, it's soluble, that's it. You don't have to do anything else, you move on. What if one of these is not involved? Then you go to rule 2, which basically says that compounds having anions with a -1 charge are soluble unless these are involved. So if it's a -1 anion, assume it's soluble. Don't tell me you have to look at it carefully if it's one of these 4. Easy to remember it, Obrickle. Make a song out of it, Obrickle, Obrickle. So for Obrickle, you have to look at it carefully because that means that there's a possibility that it's insoluble. If these 4 are not involved, -1s are always soluble. You just move on. So hydroxides, which is what the O stands for, are only soluble with alkali metals. So basically group 1, which we already covered, calcium, barium, and strontium, CBS. So if hydroxides with any of these 3, along with the alkali metals, it's going to be soluble. So any other time, it's going to be insoluble. So if I give you CuOH, copper hydroxide, copper 1 hydroxide, insoluble. Why? It's not one of these exceptions. If I give you FeOH3, once again, insoluble. Why? It's not one of these exceptions. That's the way you apply this rule. Hydroxides don't like alkali metals and CBS, so that's easy to remember it. So hydroxides do not form solids with alkali metals or CBS. CBS standing for course, calcium, barium, and strontium. Chlorides, bromines, and ions only form solids with those 3. Notice this is mercury 1. This is known as mercury 1. What is mercury 2? Without the subscript 2. That's the difference. So if you see a little subscript 2 by the mercury, it's likely to be mercury 1 unless it's got that 2 because of whatever it's attached to, which is unlikely. Silver, lead, and mercury 1. And this is lead 2, not lead 4. So don't make that mistake. These 3 will form precipitates with these 3. If these are attached to anything else, they are soluble. So if I give you NaCl, soluble. If I give you MgBr2, soluble. If I give you FeI3, soluble. The only time they're insoluble is with these 3. So keep that in mind. Easy to remember that is Brickle is a happy solid. So Brickle forms a solid with happy, mercury 1, silver, and lead 2. Compounds involving anions with -2, -3 charge are usually insoluble. The only time you have to look at it carefully is when it's sulfates. So sulfates are the opposite. Instead of being insoluble, they're actually usually soluble. The only time they're insoluble, the only time they form solids is with calcium, lead, barium, and strontium. These are the only 4 things that sulfates form solids with. Everything else is soluble. That means they don't form precipitates. So you remember it, sulfate is a solid cartoon on PBS. So sulfate likes to form solids with C, which would be calcium, PBS, which would be lead, barium, and strontium. So how to approach questions involving solubility? Look to see if the cations ammonium are group 1. If it is, it's automatically soluble. Move on with your life. If above does not apply, then focus on the anion and which rules apply. So if it's not that, then you have to look at it more carefully. And there's a whole screencast on just the solubility rules in case you need more information in this. So let's take a look at some of these. Magnesium sulfate. Well, where's magnesium and sulfate? Remember, sulfate's usually soluble unless they're with solid cartoon on PBS, right? So in this situation, that's going to be soluble and magnesium's not any of those exceptions. Barium chromate, -2 charge for chromate. We know that's usually insoluble, right? -2, -3 is just called insoluble. So this is not part of group 1 or ammonium or any part of rule 1. So that means that in this situation, this is definitely insoluble. Mercury 2 chloride. Notice there is no subscript here, so this is not mercury 1. So that means this is going to be soluble. Magnesium hydroxide, that's going to be soluble as well because it's not one of the exceptions we just talked about. Magnesium hydroxide is actually slightly insoluble, but you can get away with soluble for it. It's one of those weird halfway things. Barium sulfate is going to be insoluble. Why? It's part of the rule. Sulfates are insoluble with solid cartoons on PBS. Speaking of PBS, lead 2 sulfide, -2 charge for the sulfide. So what do we usually say with -2 charges? Insoluble. Magnesium oxide, -2 charge again, usually insoluble. So to be safe, if it's -2 or -3 charge in the anion, you could pretty much, like I'd say 90% of the time, say it's insoluble and be correct. So just keep that in the back of your mind in case you want to shortcut a little bit more, but I think this is as good a shortcut as you really need. Lead 3 phosphate, -3 charge on the phosphate because we know our polytimic ion, so that's going to be insoluble. All right, types of reactions, combination reactions 2 to 1. So anytime you see two things that are elemental forms producing one compound on the product side, you call it combination. So what you're looking for is a single product. If you have a single product, combination. Here's an example of it. Notice you have a single product, so combination. So it could be compounds on the left side, just FYI. So the best feature to look for is single product, single compound on the product side. That makes it a lot easier. Decomposition, you have a single reactant. And whatever's on the right side really doesn't matter. Just look for a single reactant. That's going to be your decomposition reactions. Both of these qualify, single reactants. Single replacement reactions, when a single solid trade's placed with a cation in a compound. So you have an element by itself in solid form, magnesium in the situation, and the magnesium and the zinc trade places. This and this trade places to produce magnesium nitrate. Notice nitrate was with zinc, now it's with magnesium. And the zinc, which was in the compound, now is by itself as a solid. So they just trade places. That's what single replacement means. Double replacement means the two cations trade places. So silver and potassium trade places. Now silver on this side is with chloride, right? Potassium was with chloride a minute ago. And potassium is with nitrate, even though nitrate was with silver before. That's what double replacement means. They trade places. Combustion reactions, the best feature to look for, oxygen is a reactant. If you have oxygen as a reactant, it's going to be combustion. You can also identify typically as carbon dioxide and H2O as your products. That's your typical combustion products. I say typical because sometimes you do produce carbon dioxide, but for our purposes, that's not going to happen. So if you have combustion with a hydrocarbon, which means a carbon hydrogen-based compound, you can assume these are the two products every time. Anytime reaction says you are burning something, it means you're reacting with oxygen. That's another tip off. So let's identify each type. You have a single product here, so that's going to be combination, obviously. For the next reaction, you have sodium bicarbonate. You notice that sodium and bicarbonate trade places, so this would be more categorized as a single replacement reaction, double replacement reaction, because they're trading places, the carbonate and the hydroxide. This reaction would be combustion because you have O2 on the reactant side. You have your CO2 and H2 as products. Calcium carbonate, single reactant, that's just simple decomposition. Net atomic equations, these are ways of writing equations out. So you have the molecular, which is everything is written out. So this is everything. You can see all the elements and their forms. The difference between that and a net ionic equation is the net ionic only deals with what is actually involved in a reaction. Not all these chemicals are reacting. Some of them are just hanging out and spectating, which we call spectator ions. So what's the net ionic equation for this? get rid of all the spectators. So silver nitrate reacts with sodium chloride to produce silver chloride. Should be I. Spectator ions. Wow, ignored. There goes spell check. That did a really bad job. Ignored. Sorry about that. All right, so you have silver nitrate. So that's up here. That's what silver nitrate looks like. Reacts with sodium chloride. Here's potassium chloride, but it doesn't really matter, to produce silver chloride. So what we did, we got rid of what's called the spectators. What are spectators? These are not involved in the reaction. We know nitrates are always soluble, so get rid of it. Sodium is group 1. That's always soluble. Get rid of it. So what are we left with? Silver and chloride ions. So that's what net ionic does. It just includes only the chemicals that are actually involved in the final reaction. Everything else is ignored. So you have silver ion plus chloride ion produces silver chloride. That's called your net ionic equation, versus you having to write it like this. Silver nitrate, this would be the molecular equation, plus sodium chloride produces AgCl plus NaNO3. So what's the difference here? We ignored what's called the spectators. Spectators are what's not involved in the reaction. So sodium is a spectator, nitrate's a spectator. Because when you write two things together, you're implying there are solids. What we really have for sodium nitrate, they're separate ions. And same thing here, we have Na plus Cl minus, and then we have Ag plus. So this is what you would actually look like in the equation, because these are all soluble, right? These four are soluble apart. Now silver and chloride like each other in the form of solid, but that's beside the point. So you see how you have nitrate on this side, nitrate on this side? If there's the same ions on both sides called spectator, you get rid of it. Same thing here. Sodium on this side, sodium ions on this side, you get rid of it. So AgCl produces AgCl. All right, types of net ionic equations. You have acid-base reactions, which are basically when you exchange a hydrogen between two elements. There are 6 strong acids. You do need to memorize them. Hydrochloric acid, hydrobromic, hydroiodic acid, nitric acid, sulfuric acid, perchloric. You do have to memorize all those. Bases, strong bases are basically compounds composed of hydroxide with group 1 metals, calcium, strontium, barium. These are basically your solubility rules. The ones that are soluble are your strong bases. Easy way to remember it. How to write net ionic equations for acid-base reactions. All you need to do is write out the reaction and then get rid of whatever is now involved. So sodium we know is always soluble. Hydrogen is involved in the acid base because this H is taken by the hydroxide. That's what acid base basically means. The acid gives a hydrogen to the base, which is hydroxide in the situation. We'll talk about that in more detail later. Chloride is not doing anything, just like Na is not, so they both go away. So that's why here I wrote everything in ionic form. And then what I did, I canceled whatever's on both sides in the same ion form. So Na goes away, Na plus, Cl minus goes away, and you're left with H plus OH minus produces H2O. That's your typical acid-base reaction for this scenario. We have a strong acid and a strong base. Oxidation reduction, where you exchange electrons between two substances. One becomes more positive, one becomes more negative. So oxidation is whenever you lose electrons. Reduction is whenever you gain electrons. Those are your two options. Rules for assigning oxidation states. There's a whole unit based on redox, so we'll talk about that in more detail, but these are just the basics. So this you do need to understand how to assign oxidation states, which is a fancy way of saying charges. So atom of an element, non-ion, has an oxidation state of 0. So anything in elemental form, like sodium is usually found as Na, solid, that's 0, mercury 0. All diatomics are 0. Remember, your diatomics are Hofbrinkel. In case you don't know what Hofbrinkel stands for, they are the symbols for the elements: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. These all exist in diatomic form, which in English means there's no H, it's H2. There's no F, there's F2. There's no N, there's N2. So if I say nitrogen reacts with something, you don't put N, you put N2. They don't like to be by themselves. Either they're in a compound or they're bonded to each other. That's the two options for diatomics. Oxidation state of any ion is the same as its charge. So if they give you a charge, that's your answer. Oxygen is -2 unless it's an H2O2. That's the only time it's -1. Any other time, it's -2. Fluorine's always a -1. Hydrogen is always a positive one in covalent compounds. These are your rules. And yes, you have to memorize them. Why? Because you need to do questions involving them. So let's take a look at this. All right, so how do you do this? What you want to do on the bottom, put the charge individually. Oxygen is -2 according to rules. There's 7 of them, so that's -14. Chromium, we're going to skip. Skip the transition metals because they have multiple charges. It's going to give you a headache. Potassium is always a +1. There's 2 of them. See what I'm doing? I'm putting the charge on the bottom, and I'm putting the overall charge. The way I get that, I multiply this number times the subscript, the charge times the subscript to get the top number. Why do I do this? Accounting. Because here's the thing, this overall compound is no charge. Why? There's no number in the right-hand corner. If this was a charge, there'd be a charge over here. If there isn't, you assume it's neutral. So overall, this next thing equals 0. I have -14 and +2. So what does this have to be? +12. Why? 12 plus 2 is 14 positive. -14 makes 0. I don't care about the top numbers. I want the bottom numbers. So what's the charge on chromium? 12 divided by 2 is +6. These are the oxidation states. These are the ones you worry about. That's how you do it. So let's do another one, KMnO4. Move it over here because it's easier to see. O is -2, 4 of them, right? -8. Potassium is +1. So what does manganese have to be? Well, +7. There's only 1 of them. So here's my oxidation state, +1, +7, and -2. Here, O, -2 still, right? 3 of them, -6. So iron has to be a +6. 6 divided by 2, +3. These are my oxidation states. Here, O is -2. What does iron have to be? +2. So there's my oxidation states again. Here, fluorine, -1, because it's always a -1, right? There's 2 of them, -2. So what do I do next? U or the O? O, of course, because there's a rule for it. -2 times -4. So times 2 is -4. So that's -6. So what does uranium have to be? +6. There's my oxidation states again. 6, +6, -2, and -1. -2. So this has to be a +2. Those are my oxidation states, +2 and -2. -2 here, 2 of them, that's -4. What does manganese have to be? +4. And that gives me 4 divided by 1, which is +4. This one's tough. When you have 2 polyatomic ions, here's my suggestion, break it apart. Ammonium's a +1, NO3 is a -1. It just makes it a lot simpler. So your O, -2. So what's the charge have to be on the nitrogen? Not +6, because remember, you're trying to get to -1 now. So it's going to be a +5. So here's my oxidation states for these two, +5 and -2. Here, hydrogen is usually a +1, right? 4 of them. So what does nitrogen have to be? -3, because -3 plus 4 gives me a +1. So here's my oxidation state. So when you have polyatomic ions, or when you have a situation where there's 2 polyatomic ions, let's say think of one. Let's go with aluminum sulfate. Excuse me, Al2SO4 3. For this, you want to break it apart too. It just makes it easier. So anytime there's more than one polyatomic ion, or there's 2 connected together, break it apart. So I would make this Al3+. At the 3+ from the aluminum, sulfate becomes SO4 -2 because of the charge in sulfate. So oxygen is -2, -8. This has to be a +6. It's the only way to do the ones that have multiple polyatomic ions. Whenever you see parentheses around the polyatomic ion, do what I just did. That's the best way to handle it. All right, last thing I'm going to cover is organic chemistry. The only thing you need to know is your functional groups. You have to memorize these. You have to know that an amide is a nitrogen bonded to a carbon and a double bond. See, these are called carbonyl groups. You know, all these have it. This. It's a common feature. You're going to look for it. So for these ones, amide is when a nitrogen is bonded to a carbon, it's double bonded to O. Ester, you have cocoa, C-O-C-O, but there's a double bonded O, but it's cocoa. Easy to remember it. Carboxylic acid, You have a double bonded O again, but now you have OH attached. That's what makes it carboxylic acid. Ketone is when you have C double bonded O and you have carbons on the left and carbons on the right. Now, it could be multiple carbons. It could be, C double bonded O, it could be CH2, CH3, it could be C. It could be any number of carbon substances. It doesn't matter. It's going to be a ketone either way. So you just look at the left, look at the right. If there are carbons on both ends, you have a ketone. Here in aldehyde, carbons on the left, so let's say this is CH3 or CH2, CH2, doesn't really matter. On the right is a hydrogen, that's an aldehyde. That's the difference. Ketone is going to be carbons on the left, carbons on the right. Aldehyde, carbons on the left, but hydrogen on the right. Amine, difference between this and amide is the amine, there's no double bonded O. That's the only difference. You don't have to worry about alkane, you're not going to see it. Ether, Coke, COC. Notice no double bonded O here either. And alcohol, anytime it's a carbon-based substances with OH. So I can make it CH3OH, I can make it CH3, CH2OH. These are all alcohols. Those are the ones you need to know. Those are the main things you have to memorize. You don't have to worry about naming them other than knowing ether is like the individual names of the compounds is not relevant. And those are all the different types once again. There's your aldehyde, carbon on the left, hydrogen on the right, double bonded O, ketone, carbons on the left, carbons on the right, carboxylic acid, carbon on the left, and an OH on the other side. There's two different ways of seeing carboxylic acid. You're going to likely see this pretty frequently, so you may want to recognize that. Has a tart taste, in case you're curious. Ester, there's your cocoa. Notice C-O-C-O, cocoa. There's your ester. Amide, double bonded O, that's your identification. What I meant by naming, you have to sit there and call this ethylamine, or that doesn't matter. Just have to recognize an amine here. This nitrogen doesn't have a carbon with double bonded O, that's why it's an amine, not amide. So amide, double bonded O to the carbon, amine doesn't have it. All right, the last thing, answering FRQs. The best way to approach this initially to get comfortable, use claim evidence and reasoning. So first thing you want to do is make your claim, answer what they're asking. So that's your claim, right? That's your answer for it. What's your evidence? Explains why your claim answers the question, uses relevant calculation or observations. This is where you put the numbers, the concepts, you incorporate it here. And your reasoning, why does that evidence support the claim? If you think like this for an average free response question, you're going to do much better on it because you're not going to sit there and leave something missing. Most common thing students do will either not answer the correct question or just answer the question without providing any support. That's a no-no. If you don't provide support, you don't get any points for your answer. So just be aware of that. You have to support everything. So if you think in terms of CR every time you do these, you have a much better time with it. So is the above an acid or base, redox or precipitation reaction? Just for your answer, that's an FRQ. So my claim is the reaction is acid-base. So I answered the question. They're asking, what is it? I said, there it is. Now, justification. My evidence is that the ammonium ion is donating a hydrogen while the hydroxide ion is accepting. That's my evidence. This is acid-base. This is how I can tell it's acid-base. You incorporate that into your answer. And then your reasoning, according to Bronsted-Lowry, this is where you name drop. Your reasoning is where you drop the names of the concept or anything that's related to answering the question into the explanation. According to Bronsted-Lowry, an acid-base reaction consists of the donation of a hydrogen from the acid to the base. There's full credit. Most students will just stop at the evidence, and then they lose points because they didn't go the extra mile and explain what the relevance of the evidence is. So start thinking in terms of what is my reasoning for the evidence. Once again, reasoning is the concepts. That's where it comes from. All right, and that's basically our